Hello, BC Calc. This is going to be your day 51 notes. For day 51, you can see we're going to do some review topics and just some more practice with U substitution. So really nothing new today. To be honest, if you hit pause right now and see what you can accomplish in this packet, I bet you could do the majority of it without my assistance at all. At least I hope so. But you can see a quick list of topics, maybe not that quick, but here's a list of topics coming up for the quiz tomorrow. We'll talk about this more next time I see you in class. Let's get right into the warm-up here. And I will have you try these as we traditionally would for a warm-up. So try numbers 1 and 2. And my hint, if you just need a little bit of help getting started in number 1, is to think fundamental theorem of calculus. Okay, so think about fundamental theorem, how we can use that to answer and figure out what f of 4 is in that one. For number 2, find the area between the x-axis and this curve. I would say for this one, it's probably a good idea to make a sketch of the graph just to make sure that you're finding the area in total. So make a sketch, see if that helps you to identify the area under the curve for number 2. So let's move on to the next page, and I will do this page with you. I like this question because it's starting to take a look at what we know about curve sketching and analyzing derivatives and different functions and their derivatives in a new graphical context. So it says the graph below is that of the function y equals g of t. So you can see y equals g of t on the domain from 0 to 4. This is used to define the function f of x as follows. So what we know is that y equals f of x is the integral from 0 to x of g of t dt. So what that tells me is that if f of x is the antiderivative of g of t, then g of t is the derivative of f of x. And I can actually prove that by using the fundamental theorem by saying, hey, if I take the derivative of f of x and then the derivative from 0 to x of g of t dt, I know that the fundamental theorem on this side would just give me g of x. And I know the derivative of f of x can be represented as f prime. So in general, the function g of x is the derivative of the function f of x. So what we're looking at here is a graph of the derivative, and I want to make some conclusions about the original function f of x. And knowing that in advance, I think will really help you to answer these questions. So where is the function y equals f of x increasing? So f of x is increasing if this is the derivative here. It's where g of t is positive. So g of t is positive where I have this positive area over here from 1 to 4. So we know that f of x is increasing on the interval from 1 to 4. For what values of x is the graph y equals f of x concave down? So if we're thinking about concave down, we're thinking about if this is the first derivative, we're thinking about where is the first derivative really decreasing. So where is g of x decreasing? And the reason why I want to figure out where that's happening is because when the slopes of the tangent lines are negative to the function g of t, that means that the second derivative would be negative, right? So I'm looking for slopes at the curve, and I'm kind of showing you in the diagram where that's going to happen. Right here, all the slopes would be positive while I'm increasing. But then the second I switch over to decreasing here, slopes of the tangent lines are negative, which means that the second derivative is negative, and the original graph f of x is concave down. So this is going to be on the interval from 2 to 4. Because of that, what is the minimum value of the function y equals f of x on this interval? So the minimum value that we can take on, now we're going to get into this concept of area. So as I plug in values for x, for the upper limit of this integral right here, the function f of x, the y value that we take on, is the accumulated area from this accumulation function. So if I plug in, let's say 0 for x, we know the integral from 0 to 0 is just 0 when those bounds match. So is 0 the least amount that this can take on? Well, not quite, because if I stop here at 1, then I have an accumulation of area that would be, since it's underneath the x-axis, it's an accumulation of -2. Can I get anything smaller than -2? Well, the answer is no, because once I move on past x equals 1, now I'm starting to accumulate positive areas between 1 and 4. So the lowest you can get is when x equals 1. So the minimum value would occur when I take the integral from 0 to 1 of g of t dt, and we know that that equals -2. So the min value that the function takes on is -2. And conversely, if I ask you for what is the maximum value that the function could take on, well, for max value, we're going to take a look at, well, we know that when I start, we're at 0. And then from there, we have a bunch of negative accumulated area. If I want to figure out the max value, what we want to do is we want to capture all of that positive area by the time I get to x equals 4. So the maximum value that our function f of x can take on is if I take on the -2, but then I go all the way to 4 and I capture that 7 as the positive area. So we're going to take the integral from 0 to 4 of g of t dt, which would be the sum of those two accumulated areas, -2 and 7, for a total value of 5. Okay, so when x is equal to 4, the output there is 5. And the nice thing about this accumulation function is that these are coordinates on the graph. The point 1 comma -2 is on the graph. So is the point 4 comma 5. And using that information and based on what we know about where the function's increasing, decreasing, concave up, concave down, you would actually be able to, if asked, make a relatively accurate sketch of what the graph of f of x looks like. So a little bit of a different look as far as given an accumulation function, which represents the derivative of f of x, how do we make conclusions about what's happening for the original function, f of x? All right, so that's what we got for that example there. Looking at the next 2 pages, these are all practice with trig integrals. So again, at this point, if you're like, you know what, I'm feeling pretty solid about trig integrals, you could actually probably stop at this point and try these on your own. I'm going to do just a few for practice, just to kind of make sure that we're, on the right track. I'll start with number 2. So for number 2, if we use the U substitution technique that we've been looking at with finding integrals, in this case, I think it would make sense based on the fact that I have x dx here to let our u just equal the inside there of x squared. Because I know that du would be 2x dx, and therefore half of du would equal x dx, which is what I have in here. So if I take that 1/2 and I pull it to the outside, it's going to be half of cosine of u du now. So the integral of cosine is sine, so we're going to get 1/2 sine of u plus c, and since u is x squared, the final answer would be 1/2 sine of x squared plus c. Now, within this video, I might make it seem easy because I can pick my u pretty quickly and easily here. But sometimes it takes some practice to get there, which is why I'm going to leave some of these blank for you to try on your own. I'm going to jump down to number 4, sine of radical x over 2 radical x dx. So what we might be noticing that is if you let u, again, kind of just equal the inside of the sine function here, if u equals radical x, the du is going to be really nice here. Because remember, this is x to the 1/2. So if I find the derivative, it would be 1/2 x to the -1/2, which is the same thing as 1 over 2 radical x. That's exactly what I have here, isn't it? 1 over 2 radical x dx is going to be what I replace with du. So this actually just becomes sine of u du because of our choice of u here. Integral of sine is negative cos u plus c, and then replace u with our radical x, and we're good. Negative cos radical x plus c is the answer to number 4. I'm going to do 2 more with you just to make sure we're on the right track for these, and number 5 is one that I'll do, sine squared 3x cos 3x dx. So in terms of making a substitution here, we've seen ones like this, and actually I think there's one just like it on the last page if you tried it already, that let's let u equal sine of 3x over here. So if I let u equal this whole quantity, then it's going to be u squared when I make that substitution. Let's kind of see if the du matches a little bit what's left over here. Well, when I find the derivative, we do have to do chain rule, right? So it's going to be 3 cos of 3x dx. And these match pretty closely, except we have that 3 out front. So if I do 1/3 du, that would equal cos of 3x dx. So now that I have that, pull the 1/3 to the front. So it's going to be 1/3 of, remember, when I do this substitution, it's u squared du now. I let u equal sine of 3x. So using the anti-power rule here, it's going to be u cubed over 3, and u cubed over 3 times a third is now u cubed over 9 plus c. So therefore, when I replace sine 3x for u, the final answer is sine cubed of 3x all over 9 plus c. All right, we're doing good here. Last one I'm going to do with you is number 7. And the reason I want to do number 7 is you're going to look at it and be like, oh no, what do I define as being u? So many of these are going to be u substitution problems, but what do I say? Let u equal tan x. Well, if u is tan x, then the derivative would be secant squared. Don't see a secant squared in here. If I let u equal the whole thing tan squared, that's not going to get any better. You're going to have to use chain rule. It's definitely not going to be leaving you something with just dx left over. So if there's no appropriate u substitution to make, then we have to go another route here. And the other route is we're going to make a substitution, but it's going to be based on a trig identity that we know. So this is not u sub here, because I don't see a du that's going to match something else that's left inside the integrand there. It's not u sub. It's going to be using the identity. Maybe you know it. 1 plus tan squared is secant squared. 1 tan's a secret. Why is that really useful to me? Because if I isolate tan squared, I get sec squared minus 1. So I'm going to replace tangent squared with secant squared minus 1. And then if I integrate both of these parts, the antiderivative of secant squared, oh wait, I know what that is. That's just tan. Minus the antiderivative of 1 is just going to be x. So don't panic when you don't find a u substitution that makes sense quickly and easily. Think about some other substitutions that we can make, namely in this case, a Pythagorean identity that allows me to find that integral. Okay. I believe all the rest, without me checking over real quick, should be examples that involve u sub, but I didn't want you to get to this one and panic and be like, uh-oh, now I don't know what I'm doing. So I'm glad that we got to number 7 here. All right, next time we're in class, we will go over the rest of these. If you want to practice with them on your own, again, you'd have more than enough practice in this lesson at least to go back and try the others. But if not, I'll give you some time in class to work on them next time I see you. Have a great rest of your day.